Myself Surojit Datta, Assistant Professor, Department of Mathematics, CNB College, Bukakhat. I am going to discuss a topic on infinite series and its convergence. Contents. We discuss definition, theorems and tests, problems, and references. Definition. If x equal to xn is a sequence in R, then the infinite series generated by x is the sequence s equal to sk defined by s1 equal to x1, s2 equal to s1 plus x2. s1 means already x1, so s2 means x1 plus x2. That means sum of the terms up to second term. Similarly, sk means sk minus 1 plus xk means sum from first term to ultimately up to kth term, x1 plus x2 plus xk. These are actually called partial sums. The number xn are called the terms and the numbers sk are called the partial sums of the series. If limit of this sequence exists, then the series is said to be convergent. Then theorems and tests. First, we discuss the nth term test. We say if the series summation xn converges, then limit xn equal to 0. That means an infinite series, if the terms gradually increasing, the sum could not be found. So actually n term gradually it diminishes and ultimately n term approaches to 0. So this test says that limit of this n term must be equal to 0. Then Cauchy criteria for series. The series summation xn converges if and only for every epsilon greater than 0 there exists m epsilon belongs to n such that if m greater than n greater than equal to m epsilon, then absolute value of sm minus sn is equal to absolute value of xn plus 1 plus xn plus 2 plus up to m term, and sum of these terms, absolute value of sum of these terms must be smaller than epsilon. Then a theorem, let xn be a sequence of non-negative real numbers, then the series summation xn converges if and only if summation n from 1 to infinity xn equal to limit sk equal to supremum of sk, k belongs to n. Some other tests, this is called comparison test. Let x equal to xn and y equal to yn be real sequences, and suppose that for some k belongs to n, we have 0 less than equal to xn less than equal to yn for n greater than equal to k. Then the convergence of summation yn implies the convergence of summation xn. The divergence of summation xn implies the divergence of summation yn. So we see that the nth term of a series is smaller than or equal to nth term of another series, and n greater than equal to a fixed natural number k. So xn less than equal to yn for all n greater than equal to k. So if summation yn converges, then summation xn must be convergent, since the terms of the sequence x is smaller than the terms of the sequence y. So the divergence of summation xn implies the divergence of summation y. Same concept is here. Then limit comparison test. Suppose that x equal to xn and y equal to yn are strictly positive sequences, and suppose that r equal to limit xn by yn exists in R. If r not equal to 0, then summation xn is convergent if and only if summation yn is convergent. If r equal to 0 and if summation yn is convergent, then summation xn is convergent. So we see that in comparison test, convergence of one series must be known. Comparing with the known series, we are able to find the convergence of the other. Now we discuss some problems. First one, so that the geometric series summation r to the power n converges when modulus of r less than 1. To prove this, let Sn equal to 1 plus r square plus r to the power n for n greater than or equal to 0. We take here the partial sum, then multiplying both sides by r. Here r is the common ratio of this geometric series. So multiplying both sides by r, we get r into Sn equal to r plus r square plus dot up to r power n plus 1, n greater than or equal to 0. Subtracting, we get Sn into 1 minus r equal to 1 minus r power n plus 1, implies Sn equal to 1 by 1 minus r minus r power n plus 1 divided by 1 minus r. So absolute value of Sn minus 1 by 1 minus r is less than or equal to absolute value of r power n plus 1 divided by absolute value of 1 minus r. As we know, modulus of r is less than 1, that means common ratio is less than 1, then r to the power n plus 1 must be 0, means approaches to 0. It follows that the geometric series converges to 1 by 1 minus r. Then another problem, it is this infinite series, it is known as P series, summation n from 1 to infinity 1 by n to the power p. Now this P series is convergent when p greater than 1 and divergent for 0 less than p less than or equal to 1. This P series is important in case of comparison tests, and we use this P series, and P series is known whether it is convergent or not. Comparing with this P series, we are able to find the convergence of the other series. Now solution, since the partial sums are monotone, it suffices to show that some subsequence of Sk is bounded. If we consider Kj equal to 2 power j minus 1 and r equal to 1 by 2 power p minus 1, then using mathematical induction we get 0 less than Skj less than 1 plus r square plus up to r power j minus 1 is less than 1 by 1 minus r, where r less than 1 as p is greater than 1. We consider first p greater than 1. Now you see, in mathematical induction we write here directly z term, but we should use gradually. So students are advised to prove it for r equal to j equal to 1, j equal to 2, etc. Then thus the sequence Sk of partial sums is bounded and thus the series is convergent. When 0 less than p less than equal to 1, we have 1 by n less than equal to 1 by n power p for n belongs to n. Since the partial sums of harmonic series is not bounded, we know summation 1 by n, it is not bounded. The partial sums of P series is also unbounded, and thus it is divergent. So P series is convergent for p greater than 1 and divergent when 0 less than p less than equal to 1. Another example, so that the series summation n from 1 to infinity 1 by n square plus n is convergent. We have 0 less than 1 by n square plus n is less than 1 by n square for all n belongs to n. Also summation 1 by n square is known to be convergent because it is P series for p equal to 2 greater than 1, hence by comparison test the given series is also convergent. Now examine the convergence of summation n from 1 to infinity 1 by n square minus n plus 1. Solution, let us take xn equal to 1 by n square minus n plus 1 and yn equal to 1 by n square. Now xn by yn equal to n square by n square minus n plus 1 equal to 1 by 1 minus 1 by n minus 1 by n square. It approaches to 1 as n goes to infinity. So we have summation n from 1 to infinity yn equal to summation n from 1 to infinity 1 by n square. This series is known to be convergent because it is a P series for p equal to 2 greater than 1. So by limit comparison test, the given series is also convergent. We give here a few examples, so we can practice more examples from these given references. First one is Introduction to Real Analysis by Bartley-Argy. Then Vedas, higher algebra, Symbolic mathematical analysis, and a textbook of higher algebra by M. Roy and S. S. Sharma. So, thank you.